Welcome back everyone. In the last lecture, we had seen observer based controller design. Now in that lecture, we had seen how to design observers, how to come up with a Leuenberger observer, and also how to design the controller gain matrix. We saw that the controller design and the observer design can be done separately because of the separation principle. Today we ask a different question. What if the system is unobservable? In the previous lecture, we had assumed that the system is observable and then we designed the observer. If the system is unobservable, what can we conclude about the system? That is what we are going to look into today. For an unobservable system, we know that the rank of the observability matrix is less than n. Now notice this means that if I try to solve an equation of the form Ox equal to 0, then rank of OAC is equal to the rank of the augmented matrix OAC 0, 0 being this here, which means that this set of equation will always exhibit or will always admit solution, and not only that, the rank of this is less than n, which means the set of linear equation of this form will always admit non-unique solution. And we already know that if you have a set of linear equation of this form, the solution of this is known as kernel of P, right? And we have already discussed that, which means that for an unobservable system, we will always get vectors which are in the kernel of OAC, and the states which are in the kernel of OAC are what are known as unobservable states. Remember from our linear algebra lecture, kernel of a matrix is a subspace, which means the kernel of the matrix OAC will also be a subspace, and this subspace, whatever elements, whatever vectors you will get in kernel of OAC are called the unobservable state. So if I take an example of this form, say A equal to -2, 1, 0, -3, B equal to 0, 1, and C equal to 0, 1. In this case, if you find out the observability matrix, the observability matrix will come out to be this. Now you can see that if I find out the solution of this equation, then what will be the solution set of this equation? The solution set of this equation will be the kernel of OAC, which is nothing but any vector of the form beta 0. Any vector of the form beta 0 will satisfy this equation, and this set is what is known as the unobservable space. Remember, in case of controllability, we had something called image of CAV, and we say that image of CAV is what is known as the controllable space. Similarly, the unobservable space is known as kernel of OAC. The kernel of OAC will give you the unobservable space. So the controllable, all the states which are controllable, if you collect everything together, controllable states together, you will get a big set, and that big set satisfies the properties of vector space. That is a controllable space. In the same way, if you collect all the unobservable states together, you will get a big set, and that set will satisfy the properties of vector space, and that set is called an unobservable space. Remember, there is nothing called an observable space. Okay, so if you take two observable states and if you add them together, you might end up in an unobservable state. However, if you take two unobservable states and if you add them together or take linear combinations of them together, the new state that you will get will also become unobservable. Okay, what do you mean by unobservable? See, it means that if I take any element, so for this example, suppose I take any element with an initial condition, suppose of the form beta 0, if I take any element like that, if you find out the output of the system with 0 0 as initial condition and beta 0 as initial condition, you will find that in both the cases the output will exactly be the same. And what is the meaning of that? Think about it. If we take an observer, right, suppose the Leuenberger observer that we have discussed, it takes input u and y, right? It takes these inputs and it gives out the estimated states. This was what a Leuenberger observer was, right? Now think about it. If the system is unobservable, which means if the system had started with beta 0 as an initial condition or 0 0 as an initial condition, the output in both the cases remains the same, and the input anyways is given by you. Okay, so that also remains the same in both cases. In that case, there is no way for the Leuenberg observer to distinguish whether the accept that will come will be because of this initial condition or because of this initial condition. So which means you will fail to estimate the actual states of the system. We have seen such an example in one of the lectures earlier itself. Let me go back to that example. If I take this example, if you see that A in this case is A is equal to a diagonal matrix of this form and C is 1 0, which means the observability matrix in this case will come out to be C and CA will be -1 0, right? Which means the unobservable space here, the unobservable space will be given by vectors of the form 0 1 beta belonging to R, right? So these are the unobservable states because unobservable states because these vectors belong to the kernel of this matrix. Now notice I will take two initial conditions in this code. The first initial condition is 0 0 and the second initial condition is 0 10. Notice that 0 10 is an unobservable state, and here I am taking my u to be a step input. This example I have already done earlier also, and notice that if I now run it, look at the output. See, the output here is exactly the same for even for x2, even for the initial condition 0 0 and for the initial condition 10 as well, 0 10 as well. Whereas the actual state, you can see x2, the actual state are not the same. Okay, I am just plotting x2 here. Okay, here we have two states x1 and x2. I am just plotting x2. So the initial condition of x2 was in one of the cases it was 0 and in the other case it was 10, right? For the 0 case also you are getting the same output, and for that case when x2 is 10, then also you are getting the same output. Now think about it from the Leuenberger observer perspective. In both the cases, if I am getting the same output and the input is also the same because the input is step input here, then how will the Leuenberger observer know for what is the actual states of the system? It won't be able to estimate the actual states of the system, and that is the problem with unobservability. I had already shown you this simulation earlier, but I am repeating it again to drive home the fact that of what is the effect of unobservability in a system. So remember, in case of uncontrollable systems, we had seen this idea that if I take a Q matrix where the first R vectors are basis vectors of image of CAV, and then we populate the matrix with new vectors such that Q is an invertible matrix, then Q inverse of AQ came out to be in this nice form. And from this form, we could tell about the controllable eigenvalues and the uncontrollable eigenvalues of the system. And this was what was known as the controllability canonical form. A similar thing can be done for the unobservable case also, and we will look into that now. So the assumption here is that the system is unobservable and the rank of OAC is equal to R, which is less than n. Okay, so in that case, we can see that the dimension of kernel of OAC must come out to be n minus R. Now, if the dimension of kernel of OAC is n minus R, then what can we tell about the number of basis vectors of kernel of OAC? There are n minus R number of basis vectors. Okay, let us say that these are the bases of kernel of OAC. Now I create a matrix of the form this, where the last n minus r vectors are the basis vectors of kernel of OAC, and the first r vectors are randomly chosen in such a way that this matrix is invertible. Remember, we did a similar kind of thing for the uncontrollable case. We took Q, then we populated the first r vectors to be the basis vectors of image of CAB, and then we extended this matrix to a full n cross n matrix in such a way that the Q matrix came out to be invertible. In the same way, here also we are doing the same thing, only difference is that we are taking the n minus r vectors which are basis of kernel of OAC at the end of the matrix. Okay, now if we take a transformation of the form qz equal to xt, we know that x dot equal to ax plus bu, y equal to cx plus du will get changed to z dot equal to q inverse of aq, z plus q inverse of bu, and y will become equal to cq z plus du. This we have been doing a lot in this course anyways, so you guys must be familiar with this idea by now. Now we will try to find out what this matrix would be, and to find that out we can write q inverse aq to be equal to a hat, okay, and then aq must be equal to qa hat. Now we will try to find out what is the structure of a hat. So a of q is equal to q of a hat, and notice now that a of p1 will give you some vector, a of p2 will give you some vector, similarly a of pr plus 1 will give you some vector. So we'll try to see what happens when we take a into pr plus 1. Now to look at that, let us try to see what is the identity OAC into a into pr plus 1. So this is the observability matrix. The observability matrix is getting multiplied with a pr plus 1. So what happens? This is the observability matrix. So a I can take inside. So this is what I get. But remember that pr plus 1 belongs to kernel of OAC. So therefore we know that it already satisfies this identity. This identity is already satisfied by pr plus 1. So which means that ca into pr plus 1 is 0, ca square into pr plus 1 is 0, and all the other terms are 0. Okay, now the important point here is what about ca to the power of n into pr plus 1, but we know that a to the power of n can be written down in this form by the Kelly-Hamilton theorem, because you know what does the Kelly-Hamilton theorem say? If a has a characteristic polynomial of the form alpha naught plus alpha 1s plus dot 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 alpha n minus 1 s to the power of n minus 1 s to the power of n, then we know that a to the power of n plus alpha n minus 1 a to the power of n minus 1 dot 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 alpha 1 a plus alpha naught I must be equal to 0, which in turn means that a to the power of n minus 1 must be equal to minus of this. So the a to the power of n can be replaced by linear combination of a to the power of n minus 1 to identity. That is what is being done here. But again, from here also we know that c times of pr plus 1 will be 0, ca times of pr plus 1 will be 0. So as a whole, everything here will turn out to be 0, which means that this vector a into pr plus 1 belongs to the kernel of OAC, because a into pr plus 1, when it multiplies OAC, the observability matrix you are getting 0. That means this vector belongs to kernel of OAC. Now if this vector belongs to kernel of OAC, what can you tell about this vector? That means if this vector belongs to kernel of OAC, this vector can be written down as linear combination of these vectors, because these vectors were basis of the kernel of OAC. Okay, so we can always do that. Similarly, if you take APR plus 2, I can write down APR plus 2 also as linear combination of these vectors. Similarly, A Pn can also be written as linear combination of these vectors. And this helps us to get to a nice form. You see, we are trying to write down AQ is equal to Q of A hat, right? And so you can see that A times of PR plus 1 will be some linear combination of these vectors. So A times of PR plus 1 is this column, you see, 0 times of P1, 0 times of P2. So beta 1 1 times of PR plus 1, beta 2 1 times of PR plus 2, and this. The same thing can be done for other vectors also, because A multiplied by Pn can also be written in this form. What about A multiplied by P1? See, P1 was an arbitrary vector that you had chosen. So A multiplied by P1 will come out to be some vector, but this vector can be written down as linear combination of all these vectors, right? Because this vectors is not special. I have chosen it arbitrarily and it is not belonging to the kernel of OAC. Okay, so we can write it down. So I am just using star here to symbolize the weights or the linear combination that will result in E of P1. So what does this give us now? This gives us a nice looking matrix of the form AQ equal to Q of this, and here you see this A hat matrix will be this now. Therefore, if I go ahead and use a matrix of this form where the last n minus r columns are nothing but the basis vectors of kernel of OAC, Q inverse of AQ comes out to be in this nice block lower triangular form. Okay, and what about CQ? Okay, now Q inverse B will be in general anything, but what about CQ? Now notice what will be CQ. So CQ is equal to again C hat, right? Now what was Q? Q was P1 up to PR, and then we had PR plus 1 dot 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 Pn. But you see, we know that C into PR plus 1 will be 0, right? So C into P1 is C of P1, C of P2 up to C of PR. But after that, from here, this will start to be 0, right? And this part we are calling as C1, and this part we are calling it as 0. Why is this 0? Because we know that PR plus 1 is in the kernel of OAC, which means C of PR plus 1 will be 0, similarly C of till C of Tn it will be 0. And that is the reason you are getting this nice form. Okay, this form actually helps us in decomposing the system into what is known as observable part and unobservable part, similar to that, like that of uncontrollable case. So let us take this example and try to decompose this system. So if you find out the observability matrix for this example, you can see that this will be the observability matrix, and you can directly see that the rank of this matrix is equal to 2, because first of all this is a 0 column, and second of all this column and this column are the same. So the only two linearly independent columns here are this and this. So the rank of this matrix will come out to be 2, and the vectors in the kernel of OAC will come out to be of this form. Because if you take any vector which is of the form beta 0 0 0, then that multiplied by this matrix will give you 0. Similarly, any vector of the form 0 beta minus beta 0 when multiplied with this matrix will give you 0. So these can be considered as a basis for the kernel of OAC. Now once we have the basis for kernel of OAC, I can create this Q matrix taking the last two rows or two columns as the basis of kernel of OAC, and in the first two columns I am choosing these arbitrarily such that this matrix is a invertible matrix. Now if we do so, let's see what happens. So we will use this Q matrix. This is your B matrix. You have the C matrix. D is 1 by 3. Q matrix, I am writing the Q matrix here. So you can see this is my A hat matrix. This is B hat, and notice in the A hat matrix you have this nice structure. Okay, you can see that there is a nice structure to the A hat matrix now. What about the C hat matrix? Let's look at that. And you can see the C hat matrix also has a nice structure. So as a whole, this is what you get. So the Q inverse AQ matrix will come out to be this, Q inverse B came out to be this, CQ was this, and D was this. And you can see that this part is AO, this is your A of UO, this part is C1, this is your 0, right? Now what are the information that we can get from this canonical form? Now notice that in this system, see, we are discussing observers, right? So for this system, we can always come up with an observer for this system, and the observer equation will follow this equation, which is the error dynamics of the Leuenberger observer. Now this equation, if I write in this canonical form, let's see how does it look like. So you see, x minus x hat is nothing but qz minus qz hat, which is nothing but the error et equal to q e hat t, e hat being the error in this canonical form. Okay, and now I can go ahead and plug this in this error dynamics equation. I'll get something like this. I can take the q to the right, we have q inverse of this expression, and then finally if I open the brackets, this is what I will get. Now I know already what is q inverse of AQ. See, q inverse of AQ is this canonical form, and q inverse of LCQ will be of this form. Why can I write it in this form? Notice that this can be written as q inverse of L can be written as, say, L1 hat and L2 hat, and we know that CQ is nothing but C10, right? And that is what is being written here. Okay, and now if I go ahead and add these up, this is what I get. This is what I get. An important thing to notice here is notice the matrix. What are the eigenvalues of this matrix? The eigenvalues of this matrix are nothing but the union of the eigenvalues of this part and the union of the eigenvalues of this part. And we also know that since this matrix that we have got, since this matrix and this matrix are related by this similarity transform, this transformation, so therefore the eigenvalues of this matrix and the eigenvalues of this matrix must be the same. This we have been doing quite a lot, so I am sure you understand this now. Okay, so since the eigenvalues are same, so that means, now notice that in this expression this part does not depend on the L value. So that means, in other words, what we are trying to say is that whatever value of L you choose, you won't be able to change the eigenvalues of this part. Okay, and that is the reason the eigenvalues of A naught, which you can change with the help of L1 hat, are known as the observable eigenvalues, and the eigenvalues of AUO are known as the unobservable eigenvalues. This is similar to what we did for the controllability canonical form, where we had a matrix of this form. And we said that we can change the eigenvalues of AC using using a control law of the form U equal to minus kz or kx hat. We could change the eigenvalues of this part of the matrix, but we could not change the eigenvalues of this. So these eigenvalues were called, the eigenvalues of this part were called the uncontrollable eigenvalues. Similarly, the eigenvalues of this part are called the unobservable eigenvalues. These are the eigenvalues I won't be able to change. These are the eigenvalues I will be able to change. Now, what does this tell us? No, notice that in case of uncontrollable case also, we say that if the eigenvalues of the uncontrollable part are on the left half of the complex plane, then the system is known as stabilizable, which means that if the uncontrollable eigenvalues are already stable, that means they are already on the left half, I do not have to think about much, because the controllable eigenvalue, if they are not even stable, then I can change, I can place those eigenvalues, or I can shift those eigenvalues to the left half of the complex plane using a state feedback controller. However, the uncontrollable eigenvalues, since I cannot change, I expect that those eigenvalues should be stable to start off with. Okay, so then we say that the system is stabilizable. The same way for an unobservable case, if unobservable eigenvalues of the system are already on the left half of the complex plane, we say that the system is detectable. Okay, And if they are not, then there is an issue, because if they are not, then the estimated states will not converge to the actual states because of the eigenvalues of the unobservable eigenvalues being on the right half plane. So we expect a system to be detectable. If a system is detectable, you can go ahead and design an observer by which you can estimate the states of the system. Now let us look at the relation between eigenvalues and poles of a system. Again, for uncontrollable systems, we had already seen that the uncontrollable eigenvalues are never the poles of a system because they do not show up in the transfer function's denominator. In the same way, for the controllable, for the unobservable case also, we can look into that. This is the unobservability canonical form. Now I can find out the transfer function of this form. The transfer function here and the transfer function coming from this will be the same. So if I go ahead and find out the transfer function from this expression, you see I will get something like this. So Si minus A hat inverse is this, and then this inverse will look something like this. I do not care what will come here, because at the end of the day, when you multiply this out, you will get an expression of this form. And notice in this expression, I can write this expression as C1 adjugate of Si minus A naught inverse B1 divided by determinant of Si minus A naught plus D, which means the denominator will not have the unobservable eigenvalues, and which means then I can say that the unobservable eigenvalues are not poles of the system. Again, like the previous case, remember, I cannot directly claim that the observable eigenvalues will be poles of the system, because there is a chance that the polynomial that you get here and the polynomial that you get at the top might cancel each other out. Okay, and in that case, one of the factors of determinant of Si minus A naught will be cancelled out. That means one of the observable poles, observable eigenvalues of the system may get cancelled out. So then that will not become a pole, right? So therefore, the only thing that I can say from this is that the unobservable eigenvalues of the system are not poles of a system. So remember, poles of a system are subsets of eigenvalues. So two things we have come up with. We know that the uncontrollable eigenvalues will never be poles and the unobservable eigenvalues will never be poles. So we have seen these two types of decomposition. In one of the decompositions, we use the P matrix in such a way that the first R vectors are basis vectors of image of CAB, and in another transformation we are using the last n minus R vectors as basis of kernel of OAC. And these two transformations gives us this one gives us the controllability canonical form, and this one will give us the observability canonical form. And from here I can read of the controllable eigenvalues, uncontrollable eigenvalues. From here I can read of the observable eigenvalues, unobservable eigenvalues. So this brings us to what is known as Kalman decomposition of a system. Now you notice that I had taken the A matrix. Okay, now the A matrix will have, say, n number of eigenvalues. Since A is an n cross n matrix, A will have n number of eigenvalues. Now among these eigenvalues, some of the eigenvalues may turn out to be controllable, some of the eigenvalues may turn out to be observable, some may turn out to be unobservable, some may turn out to be uncontrollable. Of course, that means that there can be cases when a eigenvalue can be controllable but not observable, an eigenvalue can be uncontrollable but observable. So which means the A matrix may be also divided into these four different blocks, and there exists a transformation by which we can do that, and that is the transformation that takes you to what is known as the Kalman decomposition form. I am not going to specify how to find out the transformation, but I'll just show you what the transformation looks like. You can always come up with an R matrix by which if you transform the system will look something like this. And notice in this system, if I draw the blocks, you see this part corresponds to the controllable part. You can consider this to be a B bar. So you can see that this is in this form AC, A bar 0, AUC and B bar 0 form. So this part, the top part here corresponds to controllable part, and you can see the eigenvalues of these two are the controllable eigenvalues. Okay. On the other hand, you can look at the C matrix. The C matrix in this form, if you do some permutations of the columns of this, then the C matrix can be written in this form. Now, if you permute this, that means you are permuting the variables of Z also, which means there will be permutation in the variables of this also. And if you go ahead and do this permutation, you will see that the matrix corresponding to that will have these blocks C1, C2 and 0, 0. So C1, C2 will correspond to these blocks, okay, and 0, 0 will correspond to these blocks, okay, which means that this part, these eigenvalues will be your observable eigenvalues, whereas the eigenvalues corresponding to these will be your unobservable eigenvalues. So you can see that in this transformation, we have taken everything together. It's not like a it's not like the only the uncontrollable case or only the unobservable case. In this case, everything is coming together. Okay. Now you see here the controllable eigenvalues are the union of eigenvalues of this, and the observable eigenvalues are the union of eigenvalues of this and this. Similarly, the uncontrollable eigenvalues are the eigenvalues of this part and this part, and the unobservable eigenvalues are the eigenvalues of this part and this part. Now notice that I can go ahead and find out the transfer function of this system. Now if I have to find out the transfer function of the system, I do C hat Si minus A hat inverse B hat plus D. So if I go ahead and find out the transfer function of the system, you can go ahead and do this calculation. I am not concerned about these values because these will never show up in the final expression. So if you go ahead and see the final expression will look something like this. And now notice that in this final expression, the denominator has only controllable and observable eigenvalues. That means that the poles of a system are nothing but the controllable eigenvalues of the system intersection the observable eigenvalues of the system. So only those eigenvalues which are both controllable and observable are the poles of a system. Okay. And you can see from this, we can also see that if the system is controllable and observable to start off with, okay, in that case what will happen? So if a system is both controllable and observable, you can see that the poles and eigenvalues of the system are the same, because if the system is controllable and observable, there is no uncontrollable eigenvalues, there is no unobservable eigenvalues, all the eigenvalues are both controllable and observable, which means poles and eigenvalues will be equal in that case. And such a system which is both controllable and observable is what is known as a minimal system. Okay, remember, so we had poles as subset of eigenvalues of A, right? Now if the system is controllable and observable, then poles will become equal to the eigenvalues of A. So for a system which is both controllable and observable, or in other words, for a system which is minimal, poles and eigenvalues are the same thing. So if I take this example and I ask you to find out whether this system is controllable and observable or not, you can directly look at this and say that no, this is not a minimal system, because to start off with, look at A and B, this is an uncontrollable system, so directly you can say that this is not a minimal system. Okay, then we can also ask the question whether this system is stabilizable. Let's look at that. What are the controllable eigenvalues of this system? The controllable eigenvalues system are -1, -2. So yes, the uncontrollable eigenvalues of the system are -3, -4. Yes, so which means that the system has to be stabilizable because the uncontrollable eigenvalues are on the left half of the complex plane. What about the unobservable eigenvalues? These are the unobservable eigenvalues, and both these eigenvalues are on the left half, so that means it is detectable. In this question where A has been changed, you can see that the unobservable eigenvalue, uncontrollable eigenvalues are still on the left half plane, so this is stabilizable. However, when you look at the unobservable eigenvalues, these are the unobservable eigenvalues in this case, you see that one of the unobservable eigenvalues is on the right half plane, so this is not detectable. On the other hand, in this example, you can see that it is neither stabilizable nor detectable. So, with this, we have seen that what is state feedback controllers, what are observer based state feedback controllers, and we have also seen these ideas of controllable eigenvalues, uncontrollable eigenvalues. Uncontrollable eigenvalues are the ones which will not be able to change with the help of this K matrix. Similarly, unobservable eigenvalues are the one which will not be able to change with the help of real matrix. So, if you are given a system which is both uncontrollable and unobservable, so how do we design the observer based controller? So, here is the flow. So, suppose the system is uncontrollable and unobservable. The first thing to always check is that whether it is stabilizable and detectable or not. Always check that. Okay, if it is, then we go ahead and design the controllers. So how are we going to design the controllers? Since the system is uncontrollable, so you have the AB matrix. Convert this matrix with a transformation, appropriate transformation. Convert this matrix to the form AC A bar 0 AUC and B bar 0. This we can do because we can always find out a transformation which will take us to this form. Once you have got this, you can take a smaller problem, which is basically the problem of taking AC and B bar, and then try to design a controller for this small system. Okay, once you have designed a controller, you might get something called, say, K1 hat. Use that to finally come up with a K matrix with some columns here. Okay, you have to use a transformation, and then find out the value of finally the value of K. Remember, the K hat that you will get here will have a smaller dimension compared to the K that you are looking for in this case. Okay, once you have got to the K, so you have completely designed the controller. Next, for the observer, you take A comma C and then convert this A comma C into A transpose C transpose. Once you have taken it to A transpose C transpose, this is your new system. So for this new system, then you try to find out the controller K transpose. Once you find out the K transpose, so how will you find out K transpose? Remember, since AC was unobservable to start off with, A transpose C transpose will be uncontrollable, and if A transpose C transpose is uncontrollable, you can go ahead and find out another controllability canonical form, say of this form. So a controllability canonical form of this form, then for this you can find out another, say, k1 bar controller gain. With the help of that, you go ahead and find out the K matrix, and then you convert the K matrix to K transpose to get the value of L. This will be your L. Okay, so this will be the basic flow. So if you have an uncontrollable system, first you have to go to the controllability canonical form. If you have an unobservable system, convert the system into a controller problem, and then you go to the controllability canonical form, and then after that the design process remains the same. So this will be the complete flow of observer based controller design for an uncontrollable and unobservable system.
So with this, we have learned the entire exercise of how to design observer based controllers for even uncontrollable systems as well as for unobservable systems. You should hope that your system is stabilizable and detectable so that you can go ahead and design controllers and observers. In the next lecture, we will look into something different. Till now, what we have seen is that using state feedback controllers, whether it be observer based state feedback controller or simple state feedback controller, we were changing the eigenvalues of the system to be on the left half of the complex plane, which means that we were making the system stable if the system to start off with was an unstable system. But is that enough? That is the question we are going to answer in the next lecture. Thank you.